Welcome to the video for topic 5.2, looking at the particle nature of light. So yesterday we began topic 5.1, which is looking at the wave nature of light and how it acts similar to a water wave. And now we're going to look at how light can travel as something like a particle, something that has mass. And so these two topics, topic 5.1 and 5.2, are going to start making more sense as we blend them together, but we need to kind of cover them each separately. And then the goal from here is we'll kind of mix these two things together and kind of explain why in the world we're even talking about this. So the first thing is we've mentioned briefly this word photon. And so the idea is that light can travel in these bundles called a photon. And so it's a packet, and it can be called a quantum, or plural called quanta. And so what we get from that is when you take a look and you can perceive something as green or blue or red, you are taking in different photons or bundles of light energy, and that gives you the ability to see them in distinct colors. And so photons can do a couple of things for us. One thing that they can do with a Bohr model with electrons is it allows electrons to do two things. Electrons can take in a photon, and when they take in a photon, they move to what's called an excited state. But the important thing is photons can lose that excitement, can lose that energy, and then release light, and we can perceive that in different colors. And so, like I said, that's going to tie together more tomorrow once we've built on the idea of wave side of things and energy side of things. And so electromagnetic energy, remembering that electromagnetic spectrum, it can be emitted or absorbed. So the key thing here is electrons can take in energy and move up to a specific energy level or region of the electron cloud. But the most important thing is they can lose that energy, and when they lose that energy, it has to go somewhere. So they release or emit energy, and it releases them in chunks called quanta. So it releases a specific quantity of energy, and that correlates or links to what form of electromagnetic energy it is. If it's visible light, it then correlates to a specific color of light. And so photons are unique in that they have two characteristics to them. They act like a wave, having wavelength. They can travel through space, meaning they don't need a medium, but then they also have something like a particle-like characteristic, meaning something that acts like something that has mass. And so Max Planck is kind of associated with his theory, and he started looking at the relationship between energy and frequency. So yesterday we did bring up frequency, and that frequency is looking at the number of waves passing by. We found the relationship is that as frequency increases, meaning more waves are passing by, that means your wavelength gets shorter. And the opposite can be said, that as wavelength increases, as it gets longer, your frequency is going to decrease. We talked about that being an indirect relationship, that if one goes up, the other goes down. So then Planck basically said that energy is quantized, meaning that it's a quantity, that it has a value. And so we can represent this value, this quantity, using an equation. So he has the energy formula, which finds the relationship of energy of light to its frequency. So we have a couple of things that carried over with us, and that is the Greek letter nu here for frequency. So that should be familiar, and just like yesterday, frequency is going to be in hertz. So we have two new things. We have another constant. So we have two constants in this particular unit, and this is Planck's constant. We're looking at the relationship between energy and frequency, and it's 6.626 times 10 to the negative 34 joule a second. And then that can calculate and be used to determine how much energy a light photon has, or any form of, it doesn't necessarily have to be visible light, but it could be an X-ray or anything like that, anything on the spectrum. And that can find energy in a unit called a joule. So we're going to just kind of dive right in then to our equation, working with calculating energy and working with this particular formula. So in this first problem, it says if the frequency of a ray of light is 5.09 times 10 to the 14th hertz, calculate the energy in joules of a photon emitted by an excited sodium atom. And so, like yesterday, the first thing I'm going to do is I can see it says frequency, and I can also recognize that with this unit hertz. So I know that my Greek letter nu here is going to be 5.09 times 10 to the 14th hertz. Like our speed of light constant we used in yesterday's equation, we have h for Planck's constant, and that's at 6.626 times 10 to the negative 34th joule second. And right here, it wants to know, calculate the energy. That is what we are solving for, E. So we know that E is then equal to h times frequency. And so this one is just plain straightforward. We're substituting in to solve. And so we can go ahead and plug in Planck's constant. So here we can see we have 4 significant figures times 5.09 times 10 to the 14th hertz with 3 significant figures. So we have a grand total of being allowed 3 sig figs in our final answer. So when we go through to multiply this, I get an answer of 1.38, that's my 3 sig figs, times 10 to the negative 19th joules. So that's how much energy we have here, and we'll get into this more again as we go through this particular week. Moving on to the next problem, it asks, what is the energy of a photon of electromagnetic radiation with a wavelength of 827 nanometers? What type of radiation is this? So what we need to do from here is it asks, what is the energy right off the bat? So that's what I'm solving for. And it says it has a wavelength, remember wavelength is lambda, of 827 nanometers. So in the energy equation, we have that it's Planck's constant times its frequency. Well, we know Planck's constant, that always stays with us. But the issue here is we need a frequency, and we do not have a frequency. But we do know from yesterday's equation that C is equal to lambda nu, or wavelength times frequency. So what we have here is a 2-part calculation in order to solve this problem. So what we need to do first then is work with our formula that C is equal to lambda nu. So we kind of have 2 things to solve for. So the next thing I do know is that my C is 3 times 10 to the 8th meters per second. So this one has quite a few things going on with it. So we can find frequency by dividing by lambda, where frequency is the speed of light divided by wavelength. So hopefully you kind of have caught on. The issue with this particular problem is we have meters per second, but we have our wavelength here in nanometers. That means we have a conversion that needs to take place here. So we need to get nanometers to meters to make units agree. So 1 meter is 1 times 10 to the 9th nanometers. So going through the division step here, we get an answer of 8.27 times 10 to the negative 7th meters. So I'm going to substitute that in then. So as you take a look at this, you can see that we now have meters lining up to cancel. Hopefully, again, you get in that routine that if it doesn't cancel, you know that you need to go back and make some corrections and make sure that your units are lining up to cancel. So with those canceling, and I can keep 3 sig figs, I get an answer here of 3.63 times 10 to the 14th. And this is per second, 1 over a second, or hertz for frequency. So now that gives me this piece of information, which allows me to now solve for my energy. So I then multiply that by my found calculated frequency of 3.63 times 10 to the 14th hertz. So I can go ahead and do my multiplication there in order to solve. So again, what happens here is the seconds and hertz are what's going to line up to cancel. And so then I'm left with joules, which is our unit here for energy. The Planck's constant has 4 sig figs. My frequency has 3, so that means I can only keep 3 in my final answer. So I get an answer of 2.41 times 10 to the negative 19th and joules. This one also asks, we're not done, it asks what type of radiation is this? So I'm going to lose my writing, so if you need a minute, pause the screen and get everything caught up on your notes. But we need to figure out what this is. And so I told you with the specific electromagnetic spectrum that I gave you, you want to make sure that you take a look at your handouts. So we're going to open that up. And so here we can see frequency, and we have something that's in to the 14th hertz. So that puts us in the range of probably being infrared. Okay, so we are going to go with infrared energy on that one. And we have one last problem in that we are solving for working with this equation kind of in a different way, still connecting the two problems, kind of like what we did in problem 2. So here it says an electron releases a photon containing 2.88 times 10 to the negative 19th joules. By that unit, I know that's how much energy it's releasing, so 2.88 times 10 to the negative 19th joules. It asks what is the frequency and wavelength of this radiation. And then again, identifying what it is. So the idea is we can connect our energy equation to frequency. So that means the only other thing I need to solve this first part is Planck's constant. So all I can do then is substitute in multiplying it by the provided, let's see here. I need to backtrack. So we're not solving for energy, so I'm getting ahead of myself. So in order to solve this one, we need to get frequency by itself. And to get frequency by itself, we need to divide by Planck's constant. So let me get rid of this real quick, and let's get on the right track. So when we take a look at this particular problem, we are solving for frequency again. And I need to get in pen mode. So we have that frequency is equal to the energy of the photon over Planck's constant. So we have our energy of 2.88 times 10 to the negative 19th joules, and we have Planck's constant. So we can divide this out and we can get 3 significant figures. So when we do that division step, we get that it is 3.44 times 10 to the 14th. We are finding frequency, joules cancels, and we essentially are left with 1 over a second, or a hertz. So again, just like the last problem, we now know frequency. It then asks for wavelength. So that means we then have to work with our second or first equation really in the order of things, where that our speed of light is equal to the wavelength times frequency. So we're solving for lambda or wavelength. And so we get that wavelength is equal to the speed of light divided by frequency. So the last thing we need to solve is that 3.00 times 10 to the 8th meters per second. Substituting that in, divided by our frequency of the I want to use Planck's constant, and that's not what I should be using. What I'm really using is my frequency here, which was our answer from up above. And I was just not looking at my writing close enough. So what we're actually going to plug in is this 3.44 times 10 to the 14th hertz. So from here, we have that it is 3.00 with 3 significant figures, divided by that 3.44, which also has 3 sig figs. That means we can keep 3 sig figs. So we get an answer of 8.72 times 10 to the negative 7th meters. Lining those up, hertz and the second cancels. We are finding wavelength, so meters should make sense. So again, what we've done in problem 2 and 3 is just connected the wavelength equation to the frequency equation, or energy with our speed of light equation. So if you have any questions, especially if you're having issues with your calculator, please feel free to reach out to me and I will gladly help you.